Okay, in this tutorial we're looking at section 11.3 on the binomial distribution. So when we have a Bernoulli trial that's repeated a number of times, then we get a binomial distribution. So that's made up of n Bernoulli trials or n identical trials. Each trial is an independent trial, okay, and there was always two possible outcomes for each trial. A success, which is p, or a fail, which is 1 minus p. Okay, remember the number of ways of obtaining x successes from n trials is given by ncx or n choose x. Okay, or you can write it as our big brackets here, n on top of x, which still means the same thing of n choose x. Okay, you'll find that you do have a n choose x button on your calculator. Okay, so you really would not use this formula very often here. Okay, but is equal to n factorial on n minus x factorial times x factorial. Okay, you're very rarely going to need to use that formula, okay, because you can just use your calculator to do that. If a discrete random variable x has a binomial distribution, we say that its x is a random variable that's a binomial distribution where we have n is our number of trials and p is our probability of success. Okay, so for example, you might be given something that's x is a random variable that's a binomial distribution, but we have 20 trials and the probability of success is 0.3. Okay, that's the type of thing that you'll find written. Okay, if x is a random binomial distribution, np, then p of x equals n choose x, 1 minus p to the power of n minus x, times p to the power of x, where x can be 0, 1, 2, all the way up to n. Okay, the expected value of x is equal to np, really nice and easy there. The variance of x is equal to np times 1 minus p. Okay, and therefore our standard deviation is the square root of np times 1 minus p. So we'll have a look at worked example 2. Okay, it's a bit of a wordy worked example, so I haven't worried about writing it out. Okay, but it is known that 52% of the population participates in sport on a regular basis. 5 random individuals are interviewed and asked whether they participate in sport on a regular basis. Let x be the number of people who regularly participate in sport. Okay, so we need to construct a probability distribution table for x. Okay, so what we're saying is we've got to do our x is equal to our probability of x equals x. Okay, we had 5 people, so we could have had none of them did, 1 did, 2 did, 3, 4, or 5. Okay, is what we've got there. So what we need to do basically is go through and use our formula that probability that x equals our n choose x times 1 minus p to the n minus x, p to the x. Okay, which is what we need to use. Okay, so x is the number of people who regularly participate in sport. Okay, so what we're doing here then, if we want the probability that x equals 0, then it's going to be, well, 5 choose 0. Okay, 1 minus p, well p is our 0.52, so 1 minus p is 0.48 to the n minus x, well that's 5 minus 0, which is going to be 5. Okay, and then it would be p, which is 0.52 to the power of 0. Okay, 5 choose 0 is just 1. Okay, so we end up just being, and now of course our 0.52 to the power of 0 is also 1, so it's our 0.48 to the power of 5, which gives us 0.02548. Okay, if I didn't leave myself enough room here, but this one would go in here. Okay, and we can go through and we do a probability that x equals 1. Well, this time it's going to be 5 choose 1 times 0.48 to the power of 4 times 0.52 to the power of 1. Okay, when we do that, we get 0.13802. Okay, our probability that x equals 2 is 5 choose 2, 0.48 to the 3, 0.52 to the 2. And when we do that, we get 0.29904. probability that x equals 3. Going to be 5, choose 3, 0.48 to the 2, 0.52 to the 3. Okay, when we do that, we get 0.32396. Probability that x equals 4 is going to be 5, choose 4, 0.48 to the 1, 0.52 to the 4. Okay, which equals 0.17548. And lastly, the probability that x equals 5 is going to be 5, choose 5, 0.48 to the power of 0 times 0.52 to the power of 5. Okay, and when we do that, we find that we get 0.03802. Okay, so I'm going to redraw this table because I clearly didn't leave enough room. So we need to go x and the probability that x equals x. Okay, for 0 it was 0.2548. For 1 it was 0.13802. For 2 it was 0.29904. For 3 it was 0.32396. For 4 it was 0.17548, and for 5 it was 0.03802. Okay, so we've got our probability distribution table. Okay, so that's part A taken care of. In part B, we're asked to find the probability that 3 people or less play sport. Okay, so probability that x is less than or equal to 3. Okay, so what that means is it's going to be, well, it could be 3, 2, 1, or none. So we'd say we'd add our probabilities together. Okay, the other way you could do it is say that it's 1 minus this and this. Okay, either way is acceptable. Okay, and we get 0.7865 when we do that. Okay, and of course we could use our calculator to work this out as well. Okay, for part C, what we need to do is find the probability that at least one person plays sport, given that no more than 3 people play sport. Okay, so what we're saying is we've got to find the probability that x is greater than or equal to 1, given the probability, given that x is less than 3. Okay, so what that means, okay, is that we're going to be looking at the probability that x is greater than or equal to 1, intersection of the probability that x is less than 3. Okay, and really we're looking at the overlap there, so we're saying that we're looking at the probability, okay, that we are between 1 and 3. Sorry, that was less than or equal to. Okay, so really our intersection, okay, becomes, well, the probability that's 1, 2 or 3. Okay, so 1, 2 or 3. So when we add those together we get 0.76102. Okay, but we also need to divide that by the probability that's less than 3. So this is only our top line of our equation. Okay, because remember our full equation, okay, is that when we've got that, that's the probability that x is greater than or equal to 1, intersection the probability, intersection x is less than or equal to 3 over our probability that x is less than or equal to 3. Okay, so I found that our probability for our intersection is our 0.76102, and now we've got to divide it by the probability that's less than or equal to 3. Well, we worked that out before, that's 0.7865. Okay, that means that we get a probability of 0.9676, okay, for part C. For part D, we want to find the probability that the first person interviewed plays sport, but the next two do not. Okay, so what we're saying is we've got the probability of having one person that's sport, then not sport, not sport. Okay, probability that someone plays sport, okay, is our 0.52. Okay, probability of not sport is 0.48. So this is just like if we had a big tree diagram, okay, that we're just looking at our branch that's sport, not sport, not sport. Okay, when we multiply those three together, we get a probability of 0.1198. Okay, so we'll keep moving on. We'll have a look at work example 3. Right, a test consists of 20 multiple choice questions, each with 5 alternatives for the answer. A student has not studied for the test, so she chooses the answers at random. Let x be the discrete random variable that describes the number of correct answers. Okay, we've got to find the expected number of correct answers. Okay, so our expected value, our e of x, is equal to our mu, is equal to np. Okay, well, n equals 20, probability is 0.2, okay, because we've got a 1 in 5 chance of getting it correct. So our e of x equals 20 times 0.2, which equals 4. So expected number of correct answers would be 4. Okay, I in part A is find the standard deviation correct. The correct number of questions answered correct to 4 decimal places. Okay, where our standard deviation was equal to the square root of np times 1 minus p. Okay, so that means that we've got the square root of np. Well, np is our 4. We just worked that out a minute ago. So 4 times 1 minus the probability of success, which is 0.2. That means we're going to be the square root of 4 times 0.8. Okay, so when we do that, we find that we're the square root of 3.2, okay, which equals 1.7889. Okay, and so we're done for that part. Alright, part B, a binomial random variable z has a mean of 8.4 and a variance of, so we've got a mean, so for part B, we've got a mean of 8.4, okay, and a a variance, which is equal to 3.696. Okay, we want to find the probability of success, and we want to find n. So we're going to find p and n. That's what we're looking for. Okay, well, we know that mu is equal to np. So we can say 8.4 is equal to np. Our variance, okay, is equal to 3.696. The variance is given by the formula np times 1 minus p. Okay. So we've got our two equations here. Okay, so with two unknowns, so we're basically just going to be doing simultaneous equations here. So given that np is equal to 8.4, I can sub that in straight away. 3.696 equals 8.4 times 1 minus p. So I say 3.696 divided by 8.4 is equal to 1 minus p. Okay. So when I do that, and I rearrange, right, and I say then that I have p is equal to 1 minus our 3.696 on 8.4. When we actually do that, we find that p is equal to 0.56. Okay, we can sub our p back into this equation, so we can say 8.4 equals n times 0.56. So n equals 8.4 on our 0.56. Okay, so n is going to equal 15. Okay, so we've been able to find our p and our n. Okay, so look, that's all there is for this section. Okay, they definitely put in a fair bit more information than what's really needed. They sort of go through a bit of a proof of our expected value and our variance and standard deviation, etc., from our basic way of deriving it. I just ignore that because we know what it is now, okay? So there's no point going through that too much. So you should be able to get through these questions without too much trouble, hopefully.